So welcome to this second colloquium of 2025. I will just say that the next event is scheduled for March 12, and it will be devoted to condensed matter physics. And now I leave the floor to my colleague Guilherme, who will introduce the speaker.
Okay, good afternoon, everyone. So it's my great pleasure to introduce Professor Michael Barry. So if you study quantum mechanics, he requires no introduction, but okay, let me quickly do it anyway. So Michael was an undergrad in Exeter in the UK and got his PhD at the University of St Andrews in Scotland, if I'm not mistaken. And then he was a postdoc all the way to professor, and now he's emeritus at the University of Bristol. So he spent most of his career there. So he got, well, it will be a long time here if I read all of his accolades, so I'll try to summarize them. So he was elected a Fellow of the Royal Society in 1982. He was knighted, so he's a Sir, in 1996. He got the Dirac Medal twice, one time from the Institute of Physics in the UK, one time from the ICTP in Trieste. He got the Wolf Prize in Israel in 1998 together with Aharonov, and more recently the Lawrence Medal of the Dutch Academy of Sciences. So he's a member of many national academies and gave lots of distinguished lectures and have a few honorary PhDs. So it's our great pleasure and honor to have him here today, and he's going to tell us about old and new on the geometric phase.
Good. Well, thank you very much, Guillermo, for that very generous introduction. Can you hear me? At the back, even? Just a moment. Good. I always enjoy my visits to Italy, and especially Pisa. I've been many times both invited to speak and also over many years, and also privately. My son is married to a half-Italian woman, and the wedding was nearby here. I visited last year San Miniato to hunt for truffles in the forest, also walking in Livorno, and yesterday I again explored Lucca, beautiful place, spent the whole day walking. So I like this part of the world very much. Now, this subject of geometric phases is not the easiest subject to speak about because, you know, it isn't describing as a theorist one long calculation. It isn't the discovery of a new kind of galaxy or some type of topological matter. It's a concept. And it's a concept which connects. Now, we are familiar with this in physics, but I like to quote my colleague, very distinguished colleague, Charles Frank, on this subject. Physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. It's a very deep, beautiful comment. Now, it's a subject which underneath is mathematical. And on this subject, I agree very much with Peter Atkins, who wrote in a foreword of a textbook, determining where mathematics ends and science begins is as difficult and as pointless as mapping the edge of the morning mist. Now, like many theoretical physicists, I spend my life wandering in and out of this mist, so don't ask me if this is a physics talk or a mathematics talk. If sometimes people ask me, are you a physicist or a mathematician? My answer is yes. Now, I've been told that the audience here is quite varied and not all specialist theorists knowledgeable about the subject. So this talk is a kind of technicality sandwich. The first third and the final third are not very technical, and the middle is a little bit. One more thing. As I speak, I'll occasionally mention people's names, but not systematically. But towards the end, I'll give a timeline of the tangled history of this concept. So let's go back to 1830. Almost the first geometric phase, discovered in the optics of crystals by Hamilton. Now, we all in physics, we revere the name Hamilton. We can hardly write a paper in theory without a sentence like, consider the following Hamiltonian. You know, his name is in our subject. And this is a concept, the phenomenon, that made him instantly famous. It's not so well known now, but it made him instantly famous because it used the concept that he emphasized of phase space. You would consider, in his case, trajectories of particles or rays in geometrical optics, not only in the configuration space, but also in the momentum space, which is essentially the space of directions. And it's very natural that he should find the first application, his only application, in the optics of crystals, where propagation depends on direction. I'll remind you of textbook material. In a general crystal, two beams of light travel, it's there, good, with different polarizations in any direction. And one construction he used was due to Fresnel, which is that it's the wave surface. It's a polar plot in direction space of the speeds, essentially the refractive index. Now, since there are two waves, there are two speeds, therefore two surfaces, and he realized something that Fresnel didn't realize, that what's the shape of this surface for the most general type of crystal where all three directions are different? Well, here it is, the Fresnel wave surface, and you see that the two surfaces intersect. This is half of it. They intersect at 4 points, these are directions, on two optic axes, which is why these are called biaxial crystals. Hamilton, in a very modern way of thinking, realized that these connections are special places, are singularities, as we'd say. So he looked in some detail. They're places where the two rays have the same speed. It's as though the material is isotropic in those directions. Well, he realized that each intersection is a double cone, if you zoom in. And it's the first conical intersection in physics, anticipating other ones in quantum chemistry and in condensed matter physics now. They all have the same mathematical origin. They're degeneracies of something. We'll see the something a bit later. In some areas of physics, particularly condensed matter, these are called Dirac points. That's a mistake. I mean, Dirac never drew a cone like this. He never thought of a cone in this context. And all the reasons, understandable, why they're called Dirac points were anticipated 200 years ago by Hamilton. Okay. Now, Hamilton found a very clever way to display this cone. He said, if you take a slab of biaxial crystal and cut it perpendicular to one of these axes and shine a beam of light in, a prediction will be that inside the crystal, it would spread out into a cone, a slant cone, doesn't matter why, and refract out again into a hollow cylinder of light. So if you put a screen there, he predicted you would see a bright ring. This prediction created a sensation for reason, and it's also its observation, for reasons I could go into but don't have time, but it really made him instantly famous. There are two rings, not one, and his colleague Humphrey Lloyd did the experiment a year later. Turi, this is my experiment in my little laboratory that I have at home. It's not an easy experiment, by the way, for different reasons. Now, what Humphrey Lloyd observed is that these rings are linearly polarized, and the polarization direction turns to 180 degrees. It turns through pi as you go around. So these are the polarizations. So this was, I thought originally, the first geometric phase. It's a sign change, a phase of pi, as you go round. That's the circuit. Now, it turns out it wasn't the first, and I'll tell you later what I now think really was the first, but that'll come a bit later. Okay, so phase. I don't need to tell you what phase is. Of course, it's provided you don't confuse the phase I'm speaking about, which is a cyclic change of something, For example, like the phases of the moon, its phase is naturally an angle, provided you don't confuse it with the other kind of phase. I had a student once, first-year student, who said, I don't understand this phase change of pi on reflection. Does that mean the light actually boils? Okay, so not that phase, this phase. And the geometry, well, it goes back to Gauss. The underlying geometry is parallel transport in the presence of curvature. I don't see a pointer here, but I can point. So just to remind you of how this works, I'm standing at the North Pole and I have a javelin and I'm pointing it forwards. And here it is, I'm standing at the North Pole. Now I move down to the equator, and the rule of the game is I'm never rotating this about the local vertical. It's as parallel as can be. I move around to the east or the west, and then I come back again. And when I come back, I'm pointing in a different direction. This javelin I'm pointing with has turned without ever having been rotated. How much has it turned by? Well, it's turned by an angle which is the solid angle of the path that I have traversed on the sphere. So what is this? It's global change without local change. That's parallel transport. Now, the Foucault pendulum is an example. It swings back and forth, but its plane of swing turns as the Earth rotates beneath, driving the local vertical about which it's swinging. Now, underlying parallel transport is an even deeper idea, Anholonomy, which the mathematicians with historical ignorance call holonomy. They shouldn't. Something returns after a cycle. The position of the javelin, pendulum axis, my traversal around the ring in Hamilton's conical refraction. And something else doesn't return, the orientation angle of the javelin, the swing plane of the pendulum, the polarization if you consider its direction. Many examples of this. The cat, which you drop upside down, she lands on her feet, she is turned through pi, but she's never at any stage had any angular momentum. You drop her from rest, and there's no torque acting there's from outside. And, well, what she does is she is not a rigid body. She changes her shape in the space of shapes and returns almost in the same shape, but rotated through 180 degrees. So she deforms her body, a cycle in the space of shapes. There are very simple models, Mark Levy, of how this can happen. You know, she starts vertical, she starts twisting, never any angular momentum. She keeps twisting and then she unbends. There she is. Even clearer, if it's a centipede, you bend and you twist and you unbend. No angular momentum at any stage, but turn. Another example is, you're very good in Italy at parking cars in small spaces. So imagine that you do try to park in a small space, and you do it badly. You find yourself at some distance from the edge, from the curb. You perform a series of maneuvers, steering and driving. They don't commute with each other. If they did commute, you could do all your steering in the garage before you left home. You twist and you steer and you reverse and you come forward and you're a little bit closer. And the anholonomy is this little sideways shift after your cyclic series of maneuvers. Now, you often find that you need many more of these maneuvers than you might guess. The reason is that the amount through which you shift is an area in the space of driving and steering. So if you have epsilon's worth clear space in front of you, you need 1 on epsilon squared maneuvers. Anholonomy, nice example. Now the geometric phase combines these two ideas in the physics of waves, optical waves, quantum waves, whatever. The phase is the phase of waves as they oscillate. Now, waves are one of the great themata of our subject in physics. And so we should know everything about them, and phase is their fundamental distinguishing property, so we should know everything about phase. Anholonomy is you cyclically and slowly, we discuss slowly later, change the conditions under which the waves are oscillating fast, and you return to the same condition. So you make a shift, and in light it's changing the direction of the light or changing the state of polarization. In quantum waves, you can cyclically change the forces on molecules, atoms, electrons, neutrons, photons, whatever. I have to distinguish two kinds of phase. Even if you do nothing, the wave is still waving. So there's a phase change at the end, a large phase change if you do it slowly. That's called the dynamical phase. The geometrical phase is the additional phase, which was unexpected, that comes when you make the change of the environment, changing parameters. You could say this. After a cycle, the dynamical phase answers the question, how long did your trip take? And the geometric phase answers the question, partially, where have you been? Think of it that way. You can measure geometrical phases by interference. So here's the scheme in polarization optics. For a reason, I'll describe it that way. You have incident light, you split into two, and one beam you pass through a stack of polarizers. The other beam you pass through a compensator to get nice contrast in the fringes. Then you get fringes. Now, if you twist the stack of polarizers, depending on which polarizers they are, you can shift these fringes, and the shift is by the geometric phase. Good. I'll give you a couple of examples. First of all, how do you describe polarization? On the Poincaré sphere. So this is an abstract sphere in solid-state physics, or other areas it's the Bloch sphere. In mathematics it's the Riemann sphere, it doesn't matter. North pole represents circular polarization in one direction, south pole circular in the other direction. The equator is linear polarization. All other points are elliptic polarizations, elliptic. So you change the polarization in some cyclic sequence. I've chosen one there. And then it turns out, we'll understand a bit later, that the geometric phase you acquire can be conveniently described in this framework. It's half the solid angle through which of your circuit on the unit sphere. Here's an example. This is an untwisted stack of four polar. You have to know what polarizers are projection operators. You allow one polarization, not the other. And so here it is untwisted as fringes, a millimeter. It's a kitchen table experiment. The prediction in this particular case was the geometric phase will be pi, and you see you've shifted the fringes. Now, polarizers are projection operators, but you can do the same thing with retarders, which are unitary operators. You just don't look at one of the beams. This is an untwisted stack of four retarders. Here we'd arrange things so the geometric phase is pi on 3. And here, indeed, you see this much smaller shift. Now I can tell you what I think was really the first geometric phase. Many examples of this interference. It's this. It's Fresnel and Arago in 1819, a little bit before Hamilton. Following Thomas Young's explanation that waves interfere with each other, and also that light waves have polarization, he describes it as saying that it's as though light has sides. Fresnel and Arago spent a decade understanding in very great detail the laws of interference of polarized light. There are 5 laws, and in modern textbooks you only see 4. Laws like perpendicular polarizations don't interfere with each other. Parallel polarizations do if the beams come from the same source, but not otherwise, like this. But the 5th law is almost never mentioned, and it was rediscovered a few years ago by Aurel Arteaga, looking carefully into history, and he realized it really is geometric phase. So what is it? Fresnel and Arago were puzzled by 2 very similar experiments. In the first one, you have horizontally polarized light, split into 2, rotate one plus 45 degrees, the other minus 45 degrees, and in this one you introduce a phase shift. Then you bring them back together to horizontal polarization, so you can see interference. And then you find that the intensity is cosine squared of a half delta. In the other experiment, it's the same, except that instead of resolving horizontally, you resolve to vertical polarizations. Here, again you get interference, but it's pi out of phase with the first. It's sine squared a half delta. They had some explanations which are very hard to follow, but they did realize this was a different phenomenon, and they called it their fifth law. From the point of view of the Poincare sphere, it's very easy to understand what's happening. This is what Oriol Ortega has explained. In the first experiment, you go horizontally to 45 degrees and back to horizontal in one beam, and then the other back to minus 45. And this combination has zero area, so there's zero geometric phase. But when it's vertical, vertical polarization is the antipodal point of horizontal. So you go round here to 45 degrees and then to vertical. The other one to minus 45 and vertical. So you're encountering an equator of the sphere. The solid angle is half the total, above or below, a hemisphere, which is 2 pi, half of which is pi, so it's perfectly straightforward. Oops, excuse me. Where was I? Yes, here. So that's I now think is the first geometric phase, 1819 or so. Right. Now, why? Yeah. Now, I want to distinguish the geometric phase from the topological phase. When I wrote my paper, I first, in the title, I included something like topological phase. My colleague John Hannay said, no, you mustn't call it topological, it's geometric, more general. Geometric is if the phase can take any value, like half the solid angle. Topological is if the phase is independent of the path, provided the path encloses something. For example, the Aharonov-Bohm phase, where if you do encounter the magnetic flux line, it says electrons, then the phase change doesn't depend on the path. In the or the pi phase that I've described, enclosing a degeneracy, for example, in conical refraction, the first one. So there's a difference. That's topological, and the more general is geometric. But I want to just outline what I think was the deepest application of the topological phase, was with Jonathan Robbins. And we wanted to understand the spin statistics connection. This is something quantum particles have, depending on whether their spin S is half integer or integer. And there's a change, -1 to 2s. If it's half integer, that's a sign change. Pauli exclusion is the simplest example. Now, there are many attempts in physics to derive this using ordinary old-fashioned quantum mechanics. There are arguments in relativistic quantum field theory which lead to the to this spin statistics connection. The sign change happens when you exchange two particles, or when you permute if there are more than two. But there's long been speculations, particularly by Feynman, that's a simple phenomenon. You use it all the time in contexts where you don't need field theory and you don't need relativity. Why can't you understand it in ordinary quantum mechanics? And it applies to absolutely identical quantum particles. And what we did, which had not been done properly before, we incorporated identicalness from the start in the Hilbert space of the particles, let's say 2, it works more generally, where you exchange the positions and also the spins. This is the non-trivial, it required some technology to do it. And then the exchange is a cyclic process, and it turned out, and it's a whole lecture which I won't give, that the exchange leads to this topological phase, -1 to the 2s. I'll just say a little bit more. Exchange is topological. You have two particles, let's say r and -r. You don't care where they are and how far apart, but just their relative orientation. An exchange is r goes to -r. So here's a particle, here's here's the other one, and you want to exchange them. Now, if the particles are identical, you have to identify r and -r, and the spin states, that's non-trivial. Well, when you do that, you've changed the space. It's no longer the sphere. It's something called the projective plane. It's a sphere with opposite antipodal points identified. And so, for example, you replace this point, you identify it here, and then exchange r goes to minus r is a non-contractible loop in this projective plane. So you're in the world of geometric phases, but it's topological, and you get this sign change. Now, topological phase. Why aren't we famous for having explained spin statistics in the simplest way? For the following reason. Transporting the spin means you have to use a basis different from the usual basis where you have the z-axis and you fixed and you represent the spin by its components there. No, you have to connect the spins with the positions in such a way that automatically you exchange the spins when you exchange the positions. Now, the way we first did this was very natural. It used a way of representing spin due to Schwinger, and it was very natural, and it gave the right answer. Later we discovered there are other ways we would transport the spins which lead to the wrong spin statistics relation. Now, all those other, call them perverse transported bases, there was something wrong with each of them. But we weren't able to nail down mathematically what's the natural way which gave us the result we first found, which was the correct one. So what we say is we haven't derived spin statistics using geometric phase. We've given a lot of insight into it, so we don't say we've proved it. Now comes the technical part. You know, I'm a theorist, and it wouldn't be true to my craft if I didn't show you some calculations. So we do that for a little while. So you have some Hamiltonian, depending on parameters which you change. And you have an eigenstate, let's say the nth one, discrete of that Hamiltonian. The parameters, for example, in condensed matter physics, the Bloch K vector is an example. It's a quasi-momentum. That's the relevant parameter that appears in the Hamiltonian in cases that are very popular now. And some circuit C you go around. And what's the geometric phase? There are two ways to write it. One way is it's the integral of something called a one form. One form is something that when you integrate it once you get a number, and it's the overlap of your state with a little change of the state integrated around the change, around the state. The other, which is actually deeper, and I emphasized it in my paper, is a two form. It's Stokes' theorem. A circuit integral is related to the integral of the flux of something through the circuit. So it's a double integral, and the advantage of it is that this is naturally gauge invariant. You see, when you define an eigenvector for some frozen moment, frozen of the Hamiltonian, you can choose the phase anyhow you like. And provided you choose it in some single-valued way when you come back, then the geometric phase is independent of the path. But that's not obvious here. It is obvious here, for a reason I won't go into, that it's gauge invariant object from the start. So you have to think of the space of parameters inhabited by this two-form vector in simple cases, waiting to be activated by you going around in a circuit, and then the flux of it matters, a bit like in Faraday's law in electromagnetism. Well, there's a nice way to write it, and for reasons later I'm calling it B, and you can write it as the sum over all the states that you're not considering the geometric phase of, and M here, and then you get this denominator, and it is gauge invariant because it only involves the change of the Hamiltonian. Now, here you've got this denominator, and you can see that when you're near a degeneracy, they give a very large contribution. You get a very large contribution, and this is like a monopole in parameter space, the inverse square of something, flux of a monopole, and that's where the solid angle comes in as a special case. Now, this object, however you want to define it, is interesting. There are many applications of it now, which I confess I haven't followed because after I wrote my paper I did different things. But I want to tell you about it. Here it is. Now, actually, it's equivalent to an anti-symmetric second-rank tensor field. Here it is, the I and J are the components. And so it's natural to ask, well, what about the symmetric part? Well, combined, they're part of something more general called the quantum geometric tensor. It's the only Hermitian object which is quadratic in the derivatives of the states, as I say, which is Hermitian. And it has these two parts. This is part that I've discussed from the geometric phase. It's the antisymmetric imaginary part. And the real part, well, what is it? It's the quantum geometric tensor, and it answers the question, how far apart are two states? And if you've got two states and they're the same, then the overlap is 1. If they're not the same, the overlap won't be 1. So the deviation from 1 turns out to be of this Riemannian type. Whoops, excuse me. Whoops, let's go back again. The difference, ds squared, has this Riemannian, which is why I'm using the symbol Gij. So they've got these two parts. Now, I'm a visual person, and I don't like to introduce concepts unless I can see them. So I want to show you something, examples of these structures. I'm taking a Hamiltonian made this way. Take 4 n by n matrices, keep them fixed, arbitrary, random, doesn't matter. But you include these 3 parameters, x, y, and z. So that's my parameter space. And then I look, for example, at the this quantity b, which I'm calling the curvature, by the way, for reasons that were discovered later. Well, it depends on three parameters, and the natural thing to look at is the length of this, the modulus squared. Well, I can if I fix one parameter, the z, call it 1, then I can plot the curvature. And here you see this spike. That's telling you that you're near a degeneracy. Good. Degeneracies, there's an old theorem, you need 3 parameters, an old theorem of von Neumann and Wigner. Likewise with the metric, what's a natural quantity there that you can plot? It's just the trace. Okay. And it looks the same. They're not the same, actually, but still has this spike. So it tells me that if I explore values of z nearby to 1, I should find a degeneracy. Indeed, I do. Here it is, 1.294. It goes up to 1 million. You see this degeneracy. So that's you begin to understand the structure. And similarly with the curve, with the metric. Now, something that's come quietly into physics in the last half century, with different names in different areas, is a concept of typicalness. Instead of, as I've done here, choose a special case that you can solve, sometimes analytically, sometimes not, and study it, you ask about what are properties common to all examples of a particular concept. And for that, you look at the probability distribution of, for example, the curvature, this length, where you, instead of having a single set of 4 matrices, you look at all possible matrices with some forming some natural ensemble. Different names: typicality, structural stability in mathematics, genericity. Physicists like the word universality. It's all the same, typical behaviour of something. And you ask, what's the probability distribution? There's a natural ensemble. I won't go into it. It's called Haar measure. I don't want to go into it. Okay, well, it turns out that the probability distribution of the curvature depends on whether you have a 2 by 2 matrix or more general. There's a slight change when you go from 3 to 4 to 5, but not much. It's really between 2 and the rest. There's a reason for that. Well, universally, you get this 1 on c to the 5 halves. That comes from a scaling argument, and it's to do with degeneracies. They have a disproportionate influence, and the curvature is very large there. Then the rest. Well, 2 dimensions you can solve exactly. It's this particular quantity, and I've plotted it there. More than 2 by 2 is more tricky, And you have to scale. It turns out that there's a scaling function depending on the mean curvature, and the mean curvature is some function of the dimension n by n matrices. Fine. Given that, you wonder, what's this scaling function? Well, here it is. It's this function of this quotient, small c, some function. Now, this was a horrible calculation. We had to make one or two approximations, and so we weren't totally confident that we'd captured the thing correctly. So what do? We do actually what Descartes started when he understood the rainbow and couldn't do the trigonometry. What we do now when we have a theorem, we can't rigorously do them. We do a numerical experiment. Okay, so we took an ensemble of 10,000 sets of these four matrices and actually computed this curvature distributions. And you see, it doesn't agree exactly, but it pretty well does. I mean, we pretty well captured the essence of it. So our approximation, which I am not describing to you, was decent. Now you can do the same thing with the trace of the metric tensor. I won't go into details. It's more for any 2 by 2, it's easy, and for higher than 2, but it's more complicated. I won't go through it. Right, that's the end of the technical part. Now, back again. I want to talk about these parameters that you vary as a function of time. The geometrical phase results from slow cycling of them. Fields, coiled fibers, whatever, many different ways of implementing these parameters to change the system while it's waving. So here you are, the parameters drive the system. But this is physics. The parameters are physical variables themselves, and the system that you're thinking about, the geometry, must react back on them. So we want to understand this. Now, very often, this back reaction is totally unimportant. If you're looking at, for example, a neutron experiment where you use a magnetic field and change the phase, you're not interested in the back reaction of this tiny neutron on a laboratory full of machinery. But there are some cases where the reaction does matter, and one main case is the quantum physics of molecules. What's a molecule? Well, it's nuclei. They're heavy, and they go slowly, and they drive the electrons, which are fast, much lighter and faster. So you can imagine this separation and think about the electrons. And the Born-Oppenheimer approximation, almost universal in chemistry, is that the nuclei hardly move while the electrons solve their Schrödinger equation, and their quantum energy levels depend on the positions of the nuclei. Well, quantum energies, they're called potential energy surfaces, and they act as a force field for the much slower nuclei to move when they solve their Schrödinger equation and give their energy levels. These are the vibration rotation levels, not the electronic levels that you found first. So that's an approximation, almost universal. My grandson did a PhD in theoretical chemistry, and he used density functional theory, and he was very proud. He said, I'm using fundamental first principles quantum mechanics. And I said, are you using the Born-Oppenheimer? Oh, yes, of course. Often don't think that that's an approximation themselves. Okay, but think more seriously about it. It depends on a separation of timescales. Fast electrons, slow nuclei. But it's threatened when the electron energy states get close together, and particularly degeneracies, because then transitions, etc., are slow, and you would expect Born-Oppenheimer to break down. But that's precisely where geometric phases originate. So you expect geometric phases to be associated with corrections to Born-Oppenheimer. Here's an example from the 1980s. You've got sodium-3. Here's a little cycle in the space of shapes, a tiny bit of a much larger scenario with the degeneracy in the middle, and the electron energies have a degeneracy in the middle, and a geometric phase of pi. Good, so that's what the electrons do. But you want to understand the whole molecule. So the total wave function has to be single-valued, so the nuclear quantum has to be solved with a continuation rule that around the cycle they acquire a geometric phase of, well, minus pi, which is the same as pi. And this has implications. It shifts the nuclear levels in such a way, putting it really, really crudely, you need half-integer, not integer quantization. And when you look at the spectrum in detail, which people did already in the 1980s, you can't index the levels, the nuclear levels, unless you do it in half-integer way and integer way. Now, that's old. Now, the sign change of pi is a special case. We know that already. More other systems, you have a geometric phase, which could be anything. Well, that also reacts back on the slow physics that drives it. And this reaction is the first step beyond Born-Oppenheimer, is a force of magnetic type, geometric magnetism, on the slow variables proportional to their speed. What is this geometric magnetic field influencing the slow system? Well, it's actually just the curvature that we found before. So that object has a dual role. Its flux through a circuit gives you the geometric phase, but it also describes a geometric type magnetic field on the slow variables that are being driven around the cycle. Well, there's a simple, quick and dirty way to see this happening. If you have a Hamiltonian slow kinetic energy and a fast Hamiltonian that depends parametrically on the position variables, and you look at the eigenstates, you're considering a particular fast state, instantaneous eigenstates, and then you say, well, I want to understand the slow dynamics, and a quick way is to look at the expectation value of the Hamiltonian in one of those instantaneous states. And when you do that, you have to realize that these momenta involve gradients when they act on the slow positions. And then what you get is this slow approximate Hamiltonian. Now, these two parts, the instantaneous kinetic energy, eigenenergy, and the momentum, this is Born-Oppenheimer. Then you get a vector potential A whose curl is this geometric magnetic field, magnetic gauge potential. That's geometric magnetism. There's also a scalar contribution from the metric, and here it is, this extra the trace indeed of the metric. By the way, this has a nice property. It's repulsive near degeneracy, so it acts to sort of protect Born-Oppenheimer to a certain extent. Here's an example of geometric magnetism in optics. In optics, you have a coiled ray, and it's polarized. Now, there's a result, old result. Polarization is parallel transported along the ray. So at the end, if the direction is the same as at the beginning, it's the direction that drives it, the polarization isn't the same as it was before. It's something else. Good. Now, that's the position driving the polarization. But if this object is free to move, if it's an optical fiber on a smooth surface, geometric magnetism will shift the fiber sideways, and there it is. This was discovered a number of times in the 80s and 90s and 2000 and given different names. Spin-orbit effect of light, optical Hall effect, optical Magnus effect, but they're all geometric magnetism. Well, very good. Now, you learn something from this mutuality, the driving of the fast by the slow and the reaction. It reveals the geometric phase is actually an artifact. It's an artifact of our decision to choose a system in terms of two interacting parts, fast and slow in this case. If you would consider a molecule as a whole, which you can only do for the simplest ones, and put the whole dirty Schrödinger equation on a computer, you could compute all the properties, reaction rates, energy levels, without ever considering the geometric phase. But, first of all, you can't do it except for the simplest molecule, so computationally, this separation is a good artifact, useful artifact. Secondly, exploiting this discordance, fast and slow, gives you a physical picture of what the molecule is actually doing. And more than that, taken to the limit, this quantum holism would mean that you'd have to consider the whole universe. Well, you can't do that. I mean, people talk about wave function of the universe. It's a kind of joke when they do, and they're only talking about a particular aspect of it, like the radius in cosmology or something. But still, Isaac Newton remarked, you can't understand the world if you try to understand everything all at once. You say, I'm studying this, I'm not studying that. Now, sometimes the that matters, and that's the whole world of system environment problems, of which this is one part where the environment is slow. Other examples are where it decoheres or where it's weak, but anyway, slow. Now, this separation is an approximation. Geometric phase is an approximation for driving slow compared with the fast oscillations. Geometric magnetism is the first reaction beyond Born-Oppenheimer. Now, more generally, both the phase and the forces of reaction involve an infinite series of corrections. Now, we understand the corrections for the phase. I understood that already in 1987. But the forces of reaction of the fast on the slow to get the slow variables, for a mathematical reason I won't have time to describe, is much more difficult. Now, the series of the geometric phase diverges. It has to, and we understand why. And the series for the reaction forces must also diverge, and we have some numerical examples and explorations where we begin to see this happening. But it's an unsolved problem. Good. Well, if the series both diverge, this casts doubt on how precisely fast and slow can be separated. Now, there are various techniques people are used to try to understand this. Do you actually not have a separation to infinite order, or do you have exponentially small terms which aren't captured by the power series? This is an unsolved problem. We don't know. Right. I'm not discussing this. Right. Now we come to this timeline. So let's see. 1819, Fresnel-Arago, the pi phase in interferometry. 1831, Hamilton-Lloyd, pi phase in conical refraction. 1924, Bortolotti realized that Maxwell's equations imply that in geometrical optics, polarization is parallel transported along a ray. This was rediscovered by Rytov a few years later, and it's Rytov's student, Vladimirsky, in the year I was born, who realized that parallel transport implies rotation of the polarization even after a curved ray comes back in the same direction. It's a spin redirection phase. Now, he wrote, actually, this is a deduction, but I have no idea how to do the experiment. Well, he didn't have lasers, he didn't have optical fibers. That came much later. Okay, 1956, very important work, Pancharatnam, brilliant nephew of the also brilliant but opinionated and not altogether pleasant C.V. Raman. He understood what we would now call geometric phases for two-state systems in the context of polarization optics. And he introduced a natural connection like the one form. He didn't describe it that way, but in retrospect it was. And he introduced a solid angle on the Poincare sphere. So very important work. Even though, I mean, he mentioned cycles, but his main work wasn't concerned with cycles, but still he understood a great deal. 1958, in Bristol, Longat, Higgins and colleagues, they made the first step beyond Born-Oppenheimer in molecules, because they were the people who realized that the pi sign change around the degeneracy of the electrons implies changes in the nuclear energy levels. Very important work. A year later, also in Bristol, but no evidence they talk to each other, Aharonov and Bohm discussed what we now understand as a geometric phase of electrons around a line of magnetic flux, which is inaccessible to them, but as you go round, you get a phase change. They didn't, again, think in terms of geometric phases, but it was a geometric phase that they found. 1975, totally different. Budden and Smith, they were studying radio waves propagating in the ionosphere. Now, very often you get periodic fadings of shortwave radio signals, and they realized this was interference of rays which travel along different paths of radio waves in the complicated ionosphere, and therefore you need to consider the phase. They called it phase memory. But then they found there's a little extra thing, which they called additional phase chemistry, and that's exactly the integral of this one form along the path, so geometric phase object without realizing it. Very important, 1979, Mead and Troulard generalized Longer-Higgins, and they wanted to know about the reaction on the nuclei. By looking at little infinitesimal transformations, they found what we now call the two form, the curvature. They called it molecular Aharonov-Bohm effect. 1983, my paper, I was ignorant of all of this that went before. I didn't know anything about it at all. And there's a history behind the discovery, which I won't go into. But I realized that circuits are important, and in particular the two form, the curvature, I thought was the most important mathematical object that comes. And that the fact that it's the natural origin from the time-dependent Schrödinger equation. You could derive it in that way. Barry Simon, whose paper was published before mine because of an accident of the calendar, but I showed him in 1983 my preprint, it's already with referees, and said that you might be interested in this. And he came back the next morning really excited. Yes, it's the Chern class, and it connects with quantum Hall effect, all kinds of things. So that was important. And he connected this, what I'd found, with fiber bundle theory, about which I knew nothing. And that's a nice, interesting connection. It wasn't anything new that came out, but it's still very important. And identified as curvature was something I hadn't appreciated, so that's important. Then 1984, Wilczek, let me go back, sorry. Wilczek and Z, they realized that if you have a special situation because of some symmetry, you don't have a non-degenerate state. You have a little family of degenerate states which remain all the time degenerate as you go round. Then what comes back, what they call a non-abelian case, what comes back is a little unitary matrix. These states can have transitions between one and the other, but remaining in their little subset. And that unitary matrix is the counterpart of the geometric phase when you have a family of degenerate states. My colleague John Hannay realized that for non-chaotic classical motion, you have action angle variables in classical mechanics, and the angles also would have a geometric phase, and I realized soon after how that corresponds to the quantum geometric phase for systems of that type. The angles are slightly changing. Foucault pendulum is an example of the Hannay angle. Aharonov and Anandan, very interesting development. They said, let's not consider a parameter space where you force things around. Let's consider states which, for whatever reason, in their Hilbert space, except for phase, come back. Then it doesn't matter how fast or slow you do it, you'll have a geometric phase type quantity. Now, that's very interesting, and it's certainly correct. They gave some examples, but the curvature doesn't appear in that framework. And moreover, there was what I considered then, less so now, as a disadvantage, which is that they didn't say how you make the states return. So in experiment, we do know, you do it slowly. But never mind, it was a very important development. They called it geometric phase in the projective Hilbert space. Jonathan Robbins and I, with the same Robbins, did the spin statistics, understood to some extent the geometric phase for classical systems that are chaotic, where you don't have action angle variables. I regard that as incomplete work because the formula we found is still rather mysterious. In the 2010s, Pragya Shukla and I should have said it, she was my collaborator on these calculations of the structure of the curvature and the statistics of the curvature and of the metric tensor. But we also looked at these reaction forces beyond Born-Oppenheim. We had a model, almost as simple as model you can imagine, but it was very complicated. We calculated a large number of these reaction forces and began to see the divergence of the series. And so this history leads to a question. What do you call this damn thing? Now, in we like to sometimes give names to things. Mathematicians are particularly guilty of giving names to things. It's something that repels outsiders because you have no idea, the fans of de mesure, no idea what they are unless you know the subject. But still, you could. So you could call this the Fresnel, Arago, Hampton, Lloyd, Bortolotti, Ritov, Vladimirsky, blah, 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 Budden, Smith, Hannay, Berry, Simon, Wilczek, Zeranadan, phase. Nobody would ever use that. That's why I prefer to call this thing the geometric phase. I prefer descriptive nomenclature. Now, many examples in many different areas of physics. I didn't expect this. My colleague John Hannay did, but I thought it was just some little bit of quantum mechanics that nobody would care about. But there is one paper which I like to emphasize, and it's the geometric phase of the stomach. These people realize when you digest your food, your stomach has to mix its contents. It does this by peristalsis, a cyclic sequence of maneuvers. Now, you can't, the stomach doesn't have what your food mix to have, which is a rotator. And it won't work, at least for low Reynolds number fluids, if you have a sequence of peristaltic where you change and then change back. You have to include an area in the shape, in the space of shapes of the stomach. They discuss this in some detail. They like, and then the Anholonomy is the degree of mixing after each cycle. And they looked at this in some detail. They liked my suggestion they should call this the belly phase. So now they do. Now, I want to finish by going back to the beginning, and I want to show you a way that you yourselves can easily see the geometric phase. It's a version of Hamilton's cone, but the difficult experiment with conical refraction is difficult because you can't, it's hard to get a length of crystal big enough to get decent sized rings. I could go tell you about that in some detail, but I won't. It's a way you can do it very easily. This was with Susanna Klein and Rajendra Bandari of the Raman Institute. Travelling through the crystal, the waves get out of step. And you can make them interfere with what we call a black light sandwich. So the bread in the sandwich is two polarizers, opposite. Of course, if it were a poor person's sandwich and had no filling, this would be black, because this polarizer would block what this one transmits. Well, you do have to have something. You would like to have a biaxial crystal, and they're, theorists, a little thin slab, hard to find with this. But there's another substance which we're all familiar with, those of us a certain age, which has the same property, biaxially birefringent, which is the overhead projector plastic foil we used to use when we presented our lectures. We used it without knowing, for 30 years, without knowing it's biaxially anisotropic. You don't see it under its normal function. But it is. You only need about a square centimetre, maybe 1.5 square centimetres. Many of us left over from those days have boxes of these transparencies. I mean, I make my business card by printing the transparent, use them. But anyway, this is a use. So what you do is you take one of these take a small little square and you put it between pros. What you look. Look. Now, looking is actually non-trivial. I've written a paper about looking. What is looking? You direct your gaze in a particular direction. So looking means you're seeing direction transport, and you look at the sky, not the sun, but the sky, or a white wall, or a piece of paper, and this is what you see. It's the garden of the physics department where no fancy apparatus, you just put it in front of your camera or now your smartphone, and this is what you see. Now, these fringes are the contours of separation of the sheets of a cone. You center it on a degeneracy. It takes a little bit of looking. So you're seeing the conical intersection. This black stripe is the geometric phase. You have to think about it. If you had a uniaxial material where two of those degeneracies come together, where two directions are equivalent and the third one is not, if you do that, then you would see a geometric phase of 2 pi, and it's the black cross. Mineralogists use this to identify symmetry of crystals. One thing I can't resist telling you, because you all know a certain degree of mathematics, every point in this picture, which is the direction, corresponds to a 2 by 2 matrix. the electric field of light, EXEY, comes in, electric field comes out of the slab, and that's a 2 by 2 matrix. All of these 2 by 2 matrices are non-trivial square roots of 0. Very nice for teaching, because with a number, what's the square root of 0? It's 0. But you can have matrices A, B, C, D, multiplied by A, B, C, D, that give you 0, 0, 0, 0. And for a reason I leave for you as an exercise, all these matrices, whatever you put in the sandwich, are of this type. I thought that was the end of the story. And then I had a lovely email from 2 Dutch astronomers saying, we've seen this from the window of one of the trains in the Netherlands. And they sent me this picture. Oh, sorry, before I get to that. This is the same thing, black sandwich, from the west of Ireland, looking from the little village where Stokes was born, who taught us how to measure polarization and whatever, looking across the Atlantic. It's exactly the same. But Dutch astronomers, they sent me this from a train in the Netherlands. And, well, what's that? Well, where's the sandwich? The first polarizer is the sky. The blue sky polarizes light, most strongly in the direction at right angles to the sun, which is over here somewhere. The window of the train is like the plastic sheet. Why? Because such glass is stressed when it's manufactured, making it optically anisotropic. The reason being that if you have an accident, instead of the glass shattering into sharp splinters, it shatters into a lot of blunt, almost cubes. So it's a safety thing. What about the final polarizer? Like all good physicists, they carry in their pocket a polarizer, so they just put it in front and then take a picture, and that's what they see. Now, it turns out, polarization of the sky, this was understood by Rayleigh. Here's Rayleigh. When I was young, this is what bank managers look like. Now they look like undergraduates, but never mind. Now, he died in 1919, and in 2019, his family invited some of us to visit the country house, stately home, because they were aristocrats, nothing to do with physics, Lord Rayleigh. They were dairy farmers, and it doesn't matter. And that's where he worked, to see Rayleigh's laboratory unchanged since his death in 1919. Fantastic. It's now being slowly curated. So, you know, this is where he lived. And this is where he, which he made into a laboratory, 3 floors. I'm just showing you a little bit of it there. Wonderful thing. And I was able to hold in my hand his original handwritten manuscript of the blue colour of the sky and its polarization. So it's a really beautiful thing. So I wanted to find one of my own, and British trains, you see the same phenomenon. There you are. And this again will be the end, except that I was travelling to China at the end of 2023, and I was, being a nerd, I liked to look at the moving map through, and I could see the moving. And then it was dinner time, and the instruction was, open your tray tables, and the tray table was covered with a hard sheet of plastic. When I looked in the tray table at the reflection of the moving map, I saw the geometric phase. Here it is. So it's a similar phenomenon, and this was for a slightly different time from this one, but here's the total object and its reflection upside down. It's clearer when you're flying across the sea, the Black Sea, on my way, and there you see it. So there are geometric phases everywhere. Thank you.
Questions?
Just to say 2 things about questions. First is, there are no stupid questions. Don't be shy. Secondly, I don't hear well, so I might ask you to, if I don't grasp the question, I might ask you to repeat it for me.
I was curious about the whole quantum geometric tensor, of the whole geometric tensor, because we understood a lot of the curvature, but the trace is that object that we discussed less in history. And I wanted to know in which way we can measure, we can appreciate also the trace, the real part of the tensor.
Yes, the answer is I'm not sure. It's called the Fubini-Studi metric, you probably know. So before people knew about this geometric, about the metric tensor, but of course not the connection with the geometric phase, that it's a symmetric part of something anti-symmetric, something generally Hermitian. I know that in modern condensed matter physics people do measure it. There are papers in detail measuring the metric tensor as well as the phase, as well as the. So the answer is I don't know how they do it, and I'm sorry about that. I just haven't followed. I know nothing about condensed matter. Yeah.
Okay. Thank you.
Hi. So regarding the reaction forces,
yes,
you mentioned geometric magnetism, but in classical systems you also have friction, a sort of geometric friction.
Indeed.
So can you comment on what's the difference between quantum and classical?
Indeed you can. And indeed, John Robbins and I, long ago, wrote a paper about purely classical, coupled fast and slow, which we called Geometric Magnetism and Deterministic Friction. And deterministic friction comes when the classical motion is chaotic. And then you know that you can have disorder that looks like the disorder that you have in systems of many particles, but just with small. And we had some little models, and we could calculate exactly on the average what happens. And it turns out that, of course, this effective Hamiltonian is then dissipative, and the dissipative part essentially incorporates this what in quantum mechanics is the metric, but there's a classical counterpart. So it's not not necessarily to do with quantum classical, but it's to do with disorder and not. And in quantum, you have to get this, you have to have some kind of decoherence. But it's sort of understood, although I wouldn't say even now it's totally understood. But basically, it's what I said. Yeah.
Any more questions? Okay, so there will be a reception downstairs at Sala Gran Priori, but before going there, let's thank Michael again.